This is a short video on how to calculate um, the performance characteristics for a finite population waiting line model. This model is one in which the situation being modeled has a finite number of items. For example, the copy center in the library or at FedEx office. Each only has a finite or a set number of items, that is, 4 machines, 5 machines, 10 machines. Usually the server comes to the population rather than the population arriving to the server, as in the other models we've studied. Okay, so here's the situation. Loose-knit textile mill has 4 weaving machines. Studies have shown that, on average, each machine needs adjusting every hour and that the current service person averages 7.5 minutes per adjustment. Assuming Poisson arrivals, exponential service, and a machine idle time of $40 per hour, determine if a second service person, who also averages 7.5 minutes per adjustment, should be hired at a rate of $7 per hour. We're going to assume that both people cost $7 per hour. Okay. Now we want to determine the cost of the first service person, but in order to do that, we have to determine how long, on average, a machine that requires service has to wait, and how many machines are being serviced. For this, we use the finite source model. We have 4 machines, and the service person comes to the machines to repair them. So in order for us to use this model, we need to understand some terms. N is the number of machines, in our case 4. S is the number of repairers, we have 1 or 2. T is the time required to service a machine, or 7.5 minutes. U is the average time a machine runs before requiring service, or 60 minutes. X, service factor. L, the average number of machines waiting. H, the average number of machines being serviced. And D, the probability a machine needing service will wait. And F, the efficiency factor. All of those will be calculated, and I'll show you how to do that in a minute. Okay. Okay, one service person. So that's how we begin. So first we have to calculate X, or the service factor. This number will be used to determine F, which is the efficiency factor. In turn, the service factor will help us to determine the number of machines that are down. Substituting N, S, T, and U in the equation for X, we arrive at 0.111. And we'll look that up on the table that's coming up next. This is the table that you'll be using to help us to find F. So we look for the number that comes closest to 0.111, which is 0.110. Since we have one server, we look in the S column for servers and look under 1 and go across to F, and we have the number 0.958. That number we will use in the equations to help us to determine how many machines are waiting and how many are being served. For your reference, you can find this table on page 257 in the book. And for the exam, if you need it, I'll provide it, okay? So, the cost of one server. Notice we found the 0.958 from the table. L is the number of machines that are waiting. H is the number of machines that are being serviced. So the total number of machines that are down is 0.593. Okay. This has significant implications for production and capacity planning. If you have 4 machines and 0.593 of them are down, your machine utilization suffers. In this case, 14.8% of your machines are down. This could severely reduce your production capacity. But what does it cost to have one service person? Okay, we take the 0.593 times $40, and that's the machine down cost of $23.72. Then we have to add the labor cost of $7 per hour for the one server. So therefore, the total cost is $30.72. Now that we know how much it costs per hour for one server, how much does it cost for two? We do the same thing. We find 0.110 in column marked X, and then we move over to column F and we find 0.998 for two servers because we look in S equal to 2. We add these two numbers and we arrive at the total machine number of machines down as 0.451. That's a slight drop, right? But then we also have to consider the machine down cost for two servers. That's 0.451 times $40 or $18.40. But then the labor cost doubles. So we have a labor cost of $14. So the total cost of two service persons is $32.04. The incremental cost of a second service person is $1.32 per hour. And the percentage of the machines down becomes 11.3%. As the manager, you'll decide whether this incremental cost is worth the number of machines being out of commission or not. That's where the decision making comes in. So in summary, waiting line models give us information we can use to assist in making decisions. In this case, the decision will probably be based on how critical these four machines are to the firm's productivity, capacity, and of course profitability. If it is a slack time without a lot of jobs to complete, having these machines down may be okay. But if it's a busy time of the year or they are in the middle of a very important job, they will get these machines back up and running as soon as they possibly can. So that is the end of this video on the finite population waiting model.